Welcome everyone to 1.2, which I promise, if you survived 1.1, you'll probably be able to survive the rest. You'll be able to survive 1.2. Okay, this section is not as bad as the first one. That first section's a notoriously messy and tedious section for a lot of calc classes. So this one to get a little bit better. We're moving in the right direction. Think of the last section that we did as kind of, if you remember the limit definition of the derivative, the limit of as h approaches 0 of f of x plus h minus f of x all over h, if you remember that. That's kind of what last section was. So now we're getting into some more interesting stuff, and we're going to start moving on that way. And specifically, we're going to finally talk, I mean, it was only one section, so it wasn't that long, but we're going to talk about what an integral actually is. So chapter 1 is integration. And in fact, most of calculus is integration, but we haven't talked about what an integral is. But we're going to start just a little bit by talking about one kind of integral, specifically the definite integral. And eventually we'll talk about an indefinite integral, as you might expect. Okay, so that's what we're going on, and we're going to start with a little trip down memory lane. Now, hopefully we're not going down far in memory lane. We're just mentioning a little bit about what we talked about in the last video. So you should have this from before, that the area under a curve is the limit as n goes to infinity. And remember, n was just how many rectangles, how many subintervals we divided the interval. Think of n as the number of rectangles. The sum from the first rectangle all the way to the nth rectangle. So we're summing n rectangles and taking n to infinity of the function value. And this x sub I star was just any point in that little subinterval. Sometimes we chose the leftmost point. Sometimes we chose the rightmost point. Sometimes we chose the point that made it the biggest or the smallest. But in general, x sub I star is just any point in that interval. So this is just the height of the rectangle times this thing called delta x, which is just the width of the rectangle. All right, so we're just adding up n rectangles. They have heights and widths. The height's determined by the function. And as that n, number of rectangles, goes to infinity, that's the area. And we had a cool visualization of this as well. Remember over here, right? These are all these different Riemann sums. So this is a Riemann sum with 1, 2. I'm just going to cheat. It says 10 or something. 10 rectangles. Right here is an approximation for the area under the curve. And as that number of rectangles increases, as n is going to infinity, we're getting more and more rectangles. The rectangles are getting thinner. And notice that the height of the rectangle is always just that function value at that point. Here, the point they used in a subinterval was the midpoint of each subinterval. And that's why you can see it easier over here, right? Oh, or even here. The height is the function value at the midpoint of the interval. And that's what we talked about really in the last video, and that's what we're going to connect to a new topic in this one. So let's really get into the new stuff. We're going to start with a definition. All right. A definition. Let's say if f is defined on the interval from a to b, we need that because if it's not defined, well, a lot of weird things can happen. Then we say the definite integral. Oh, we're starting right with the definition. Oops, that's definite integral of f from a to b is the integral from a to b. This is like that sign on the side of the cello. People see it a lot. You'll see the integral sign lots of places. Looks like kind of like a big S. The integral from a to b of f of x dx is just this a. It's just this. The definite integral is the area under the curve. It's the limit. N goes to infinity of the sum. I'm just copying down that same exact thing that I wrote right above. That's the definite integral. And there's a part 2 of this definition that there's not room for right now, so I want to make a couple more comments. So these a and b's, these are what are called the limits of integration. Meaning we're just going from a to b. Okay? This f of x part, that's the function. That's like the height of each rectangle. And that's what's called the integrand. And the dx really just means that x is our variable. Just like, if you remember, when we looked at derivatives, d dx meant derivative with respect to x. d dy was derivative with respect to y. d dt was derivative with respect to t. So it's the same idea here. It's not a coincidence, all right? This says we're integrating with respect to x. Okay? So now, before I go to part 2 of the definition, I want to say that this left-hand side and this right-hand side are essentially, they have the same pieces. Okay? Let's look at this first piece. The sum from the first piece, I equals 1, to the last piece, n. Well, all an integral really is summing infinitely tiny pieces. So this left part is also like a sum. I think this part and this part look pretty similar as well. All right, this is just the height. This is the function value. And then these last parts are really quite the same as well. The dx is kind of like an infinitely tiny width. And so that's what's going on here, and that's how you can think of a definite integral as basically just adding up an infinite number of infinitely tiny things with these heights. And the heights are just the function at all these different points in the interval. All right, we'll be using a lot of this, so don't worry if it's not familiar or comfortable yet. Second part of the definition, so write this right below. Provided the limit exists. Right? An integral is just a limit. Just like a derivative is just a limit. Remember that limit definition of a derivative. A derivative is just a limit. It's the slope. Integral is also a limit, and it's an area. We've talked a couple ways about why this integral is an area. We'll talk about some more and really drive that home as well in the upcoming sections, the whole class really. And the final part of this definition, in which case we say f is integrable on that interval. Okay, so that's part 2 of the definition. If we can take the derivative, it's differentiable. If we can take the integral, it's integrable. Okay, so we're not particularly creative with our definitions here in math land, but here we are. Okay, so let's answer the natural question here. I bet a bunch of people are wondering right now. Well, you say provided the limit exists. Well, what happens if the limit doesn't exist? What is that going to look like? Well, to do that, we can just look at. I'm sure everyone was asking that question. To do that, let's look at 2 functions. Okay, let's look at the function 1 over x and a very similar function that is so similar I can't even draw the differences. It's got a slightly different shape, but y equals the square root of 1 over x. All right, now area is the definite integral. So if let's say this is 1, then the integral from 0 to 1 is the area from 0 to 1. Well, it turns out in this first one, the integral from 0 to 1 of 1 over x dx doesn't exist. The limit doesn't exist. This is infinitely much area because there's an asymptote. Well, not just because there's an asymptote, but there is an asymptote. This is infinitely big. You know what this is? It's not infinite. We just have to change this shape a little bit. All right, hold on. I'm changing the plan. I'm changing the plan. I want to show you the actual difference. Okay, they look pretty similar, but let's show you the actual difference. 1 over x, that has infinite area between 0 and 1. And 1 over the square root of x, this blue one, does not have infinite area. Look from 0 to 1. And then maybe from, maybe go up to 10 or something. So the blue graph is not infinite between 0 and 1 area, but the red graph is. You can see that, yeah, they're the same shape kind of, but the blue graph is going to be a smaller area, right? It's over here. Underneath the red graph, infinitely much. Underneath the blue graph is, it still has an asymptote. This blue graph still doesn't touch. And in fact, it will never hit the y-axis here. Sorry, this blue graph, they're both blue. This one doesn't hit the y-axis. That is an area of 2. This area, infinitely big. This area, slightly different shape, but still has an asymptote, still goes off to infinity. Area is 2. So it's kind of funny. There's some weird things like that in math. Okay, let's do some problems. So that's all the material for this first video. Now just some example problems. And instead of doing example problems that the book has, which is usually what I do, I decided to do some example problems that were more related to the homework. Now normally, this is important, normally I don't want my examples to be exactly the same as the homework because I want you to have to apply what you've learned, apply the topics to what you've learned to do the homework. But here, these problems themselves are pretty weird. And so I want to make it a little bit more attainable for you. Okay, so example 1. This is actually number 62 in the textbook. If you would like, express the limit as n goes to infinity of the sum I equals 1 to n of sine squared of 2 pi x sub I star delta x over the interval from 0 to 1 as an integral. So right off the bat, this looks way harder than it actually is. So let's just think back. Go back to our notes about what is an integral. And in fact, I'm going to write it down again. The integral from a to b of some function with respect to x is just the limit of Riemann sums. The limit of the sum from I equals 1 to, not infinity, to n f of x sub I star delta x. So all we have to do is match the pieces. Let's just match the pieces and we'll have our answer. Our final answer should look something like this. All right, so right off the bat, this should be that. Let's compare them. Well, the limit parts are identical, right? In fact, the sum parts are identical too. Okay, so we've got... let's start with the easier part, right? They both have a delta x. Those are identical too. In fact, everything underlined in blue, is identical to our definition. So that means that most of this stuff is just going to be a straight direct translation, right? We're still doing things with respect to x, and we have our integral. All we need is what is a, what's b, and what's f. All right. So here's what's different. These green things look a little different. So how can we correlate them? F of x sub I star is sine squared of 2 pi x sub I star. Right? The green things are going to be the same because it's a definite integral. All the blue stuff is identical, and in fact, the green stuff is the same. Just here it's with function notation, and here it tells you what it actually equals. All right? So if this is the case, which it has to be, well, then in that case, what is our function? Okay, we need these green things to match up. So the sine squared of blah, blah, blah has to be the function evaluated at this x sub I star. Well, the only difference between these two things is one is the general function and one's the function evaluated at a specific point. So all the function is basically this, but not at x sub I star, at any x. So our function here is the sine squared of 2 pi x. And remember, this is just evaluating a function. This is just plugging in, replacing all the x's with x sub I star. So it looks super messy, but we've basically already finished the whole problem. The blue underlined stuff is exactly the same, nothing to worry about there. Only thing is, how can we relate the green underlined stuff? Well, they should be the same. And this is just a function with function notation. This is our actual function. All we need is the general function. And now we can just plug things in. Now let's look at this yellow guy and copy it over. We have the integral from a to b. Oh, what are our limits of integration? What's a? What's b? Well, go back. A and b are just, what region are we integrating over here, right? Here a and b was 0 and 1. We were integrating, hi October. We were integrating between 0 and 1. Well, what region are we integrating over here? Well, it's also 0 and 1. Great. What's next in this yellow underline? The function. Well, we already did that. We already said what the function is, so let's just replace it. The function f of x is sine squared of 2 pi x. What's next? The dx. Well, yeah, we're taking the integral with respect to x. X is our variable. So we're not going to change it to a dy or a dt, which will happen sometimes, but we're not going to change it like that now because x is our variable. That's it. That's our answer. This integral is exactly the same as this Riemann sum as the limit goes to infinity. As we get infinitely many pieces, this sum up there is going to equal this definite integral. They are the same thing. This integral is an area. And the area is the limit as we get infinitely many tinier and tinier rectangles over that region. And that's what this video is all about. Let's get some more practice. If you want, you can start immediately on the homework. You don't have to finish the video. But if you want more practice, I'll do another example. And you also have the selected homework problems video in 1.2.5. Okay? Another good strategy, if you're being adventurous, is you could pause the video after I write down the example. These are also directly from the textbook. And you can try them on your own and see if you can get them. But they're tricky. So it's all right if you can't. So given L sub n or R sub n, remember these are the Riemann sums with n rectangles, where those rectangle heights are either decided from the left endpoint of each subinterval or the right endpoint of each subinterval. Express the limit as n goes to infinity as a definite integral. So we're really just doing the same thing. Part A is going to be number 65 in the homework. And that's R sub n is equal to 1 over n times the sum, I goes from 1 to n, of I over n. And now you might say, Jason, you said this is the same as the last problem. This doesn't look the same. But it is. It is. Remember, I'm going to copy it down again. The definite integral is the integral from a to b of whatever our function is with respect to x. And that's the limit as n goes to infinity of the sum of the n rectangles. And the height is the function evaluated at some point in that subinterval times the width of the interval. All right. Now, it's the same, but it's kind of harder, okay? I'm not gonna kid you guys. These ones can be tricky. So now what we need to do is, again, so the limit as n goes to infinity. So the problem already takes care of that part. If n goes to infinity, how are these two the same? How are these blue things the same? Okay, let's just start piece by piece. This and this, literally identical. Delta x, just like last problem, is usually where we start next. I don't see a delta x. And it's not this. Delta x is the width of our interval. And in general, we have every interval be the same width. Well, if there are n rectangles, and each rectangle is the same width, what's the width of the rectangle? Well, it depends on the interval. But this looks like a likely candidate. But you might say, Jason, these green underlined things aren't in the same spot. Remember 1.1.1, properties of sigma notation. And that this is exactly the same as that. 1 over n is a constant. It doesn't depend on I. So we can put this whole thing in, or we could take this n, we could factor that out. That doesn't help us to factor it out, but we could. The only thing that can't move around is the I, because the I is stuck in here. Because the sigma notation has to do with i's. So we could write it like this. And now all of these green underlines mean the same thing. The width of each little rectangle in our little picture is 1 over n. And that's useful. We'll get to why that's useful in the meantime. And now, the blue underlined things are exactly the same. All of the things underlined in blue are exactly the same. All the things underlined in green are exactly the same. So if this is indeed a sum, then that means that these yellow guys are actually exactly the same. And again, this is where things really get tricky. This yellow step is the hardest step. This tells us that f of x sub I star is equal to I over n. Also, I wish yellow and green didn't look so similar to me. These are harder. I never thought of myself as colorblind, but once I started rock climbing, I realized that maybe I'm not as good at differentiating colors as I would like to be. So here this is. So think about all the different rectangles. I is going from 1 all the way to n. This is the height of the ith. I don't know how you write that. Ith. The ith rectangle. And it's the function evaluated at the location of that rectangle. All right. So the first rectangle, right? Let's just list some of these out, right? This is true for any I between 1 and n. Let's just list these out. The first one is going to have height 1 over n. And the second one is going to have height 2 over n. The third one's going to have height 3 over n. And the last one is going to have a height n over n, which is 1. In this case, this one's maybe even a little harder to see than part B is, even though it looks like an easier problem. The height is actually just the location. The function is the identity function. F of x equals itself, x. F of x equals the input, x. Okay, so in fact, these are actually the x sub I stars. That's the first one. That's the second one. And that's actually the last location. That'll be easier to see once we do another problem, so don't worry about this too much. And this tells us that the function's the identity function. All right, because this is that. And if the function is just the input, then that's the identity function. And that tells us most of the pieces. So we need to write this as a definite integral. And hold on with me, we'll do another example problem. This is confusing, weird kind of stuff. We don't know a and b yet. We're close. But let's skip that part for now. We know the function's the identity function. F of x equals x. And we know that our variable is x. And again, this blue corresponds to this blue. This green corresponds to this green. And the yellow corresponds to the yellow. So the last thing is, what are our limits of integration? Well, as n goes to infinity, what's happening? As n goes to infinity, our first piece is 0. As n gets infinitely big, this first piece basically becomes 0. What's our last piece look like? As n gets infinite, well, it doesn't matter what n is. The last piece is always 1. So this is really just finding the integral, the area under the curve of y equals x from 0 to 1. Let's do another problem to sort of formalize this process. And I actually think part B, even though it's a messier problem, is actually easier to see what's happening. All right, let's do part B. Part B is going to be number 66 in the textbook. That's going to be L sub n equals 2 over n. The sum, I goes from 1 to n, of 1 plus 2 times I minus 1 over n. All right. So it may also help to go back to your notes from the first section of this class. In the notes for the first section of this class, during that really long, messy video, there were 2 of them, but during one of those long, messy videos, we had a formula that said the left endpoint is the sum from I equals 1 to n of the function. Now, for any Riemann sum, we have x sub I star. It doesn't matter where in the subinterval we are. But if we're specifically a left endpoint, then it's going to be at the I minus 1th x location. Delta x. So this is one way to make things maybe a little bit easier, because for left endpoints, you're going to see this similarity here. Okay, so let's do the same process. All right, so what is delta x? Well, just with the same logic as last time, delta x, did I use green for delta x? I did, good. Delta x is just 2 over n. And that immediately is going to tell us the width of our interval. Why? Because there are n rectangles, and if each rectangle is 2 divided by n in width, that means the total width of our interval has to be 2. If it were 3 over n rectangles, each one 3 over n, total width is going to be all of that together, 3 over n times n, 3. Okay, so these green things are indeed the same. And the yellow things are going to be the same as well. So what are our x sub I minus 1s? And what's our function? What is f of x sub I minus 1? And what is... And then really, this is also useful, but because we eventually want that integral of that function. Well, we know this first one immediately, because the underlined yellow thing is the underlined yellow thing. They are the same. So let's copy that down. It's 1 plus 2 times I minus 1 over n. So now, using our logic from last time, that's the function evaluated at this x location. Well, just like before, this is just x value on that ith minus 1th subinterval. So this is going to be I minus 1 over n right here. And the function is just 1 plus 2 times that thing. Look how it all fits together. And we can visualize this as well. Before I finish, let's finish it and then I'll visualize it to make things hopefully be a little bit clearer. So again, we have the integral. We know the width is 2, but we don't know where we're starting necessarily. So let's just look at some of these. Where's the first one? Where's the first one? Actually, I guess the first one is going to be when I is 1. When I is 1, we get x sub 0. When I is 1, we get 1 minus 1 over n. First one is at 0. Where's the last one? That's when I is n. It's going to be at n minus 1 over n. So as a number of these rectangles goes off to infinity, as n goes off to infinity, the first rectangle starts at 0, and the last rectangle, as n goes to infinity, n minus 1 over n. Oh, wait a minute. Oh, no. I made a mistake. Made a mistake. So here's the problem. And this is a good problem-solving way. This is a good way to approach a problem. Even though I made a mistake, it's still a good way to approach a problem. Well, this, as n goes to infinity, was 1. But I know our interval can't be from 0 to 1. Why is that? Because we said the width of our interval had to be 2. So I guessed that this was our x sub I minus 1, which gave us this as our function. And that's a perfectly good guess. We know it's not true, though, because of this. So start with a guess, just like a lot of calculus, and then refine it. This would only give us an interval of size 1. We need an interval of size 2, so what we're going to do is modify it. That's our x sub I minus 1. So that is now the nth term. And as n goes to infinity, that is now 2. And we're good to go. But if we update our x sub I minus 1, that also updates our function. What's our new function? Well, it's going to be 1 plus this. And this is our x. So our function is actually just 1 plus x here. So this is a perfect opportunity to show the problem-solving strategy and show how all the pieces need to fit together, because sometimes you make a guess, and sometimes it doesn't turn out to be correct. So this is our function. Our function is 1 plus x dx. And as x goes to infinity, these two things should indeed be equal. All right? And that's the tricky part of this. Probably one of the hardest parts of chapter 1 is this video and then those two messy videos from the last one. That's why they're so long, because I don't like having long videos, but some of the topics are just messy enough that I need to spend some more time with them, okay? So we'll do more practice problems in the last video of this section. It should set you up for this part. And these are good conceptual videos, especially for those of you going into more theoretical aspects of science or math. But for people going into more practical aspects, the rest of the videos for this section are going to be more applicable and frankly, much simpler. Okay, so this is where I'll leave you for now, but feel free to let me know if you have any questions, and good luck.